Hey, Nathan here. Welcome back to another video game artificial intelligence video. In this video, we are going to discuss the algorithm behind improving the wandering steering behavior. So I decided to split this video into two. I was going to discuss the algorithm in the beginning of the video and then go into the coding, but we'll have the dedicated video for coding in the next video. For this video, we'll just discuss the algorithm so we can go into more detail instead of rushing through that. Okay, so the whole goal for this wandering steering behavior enhancement is to improve on the existing algorithm where we just did a random angle, a random delta angle for the object to travel, and then we would lerp to that new angle. So we're going to improve on that, not only by improving on the basic algorithm to wander, but we're also going to improve on it by influencing the object's direction to locations it has never been to before. So the first thing we need to do is to improve on the basic algorithm, not just doing a random delta angle and lerping to that new position. We're going to do things a little bit more standard with the wandering steering behavior. So the basic idea is to any object we have that's moving has a velocity in our game. Velocity is the length of the velocity vector is determined by the object's speed. So wherever the object's traveling, that's where the velocity vector is pointing to. We are going to extend a imaginary circle in front of our object at the same angle that the velocity vector is pointing. So we don't want the circle behind our object, we want it directly in front of our object where we're traveling, and that is controlled by a length that we'll call the circle distance. So the farther away the circle distance is, the smaller the delta angle will be. So the smaller the object will kind of rotate back and forth and give that little of a wobbling effect to it. We're also going to have, so that imaginary circle, we're also going to randomize a angle between 0 and 2 pi. So between 0 and 2 pi, that's a full circle. We're going to randomize an angle between that, and then we'll choose that point on the circle. And that will be controlled by a value that we'll set as the circle radius. So once we have the point on the circle, now we get to, from our player's position to that point on the circle, that is where we want the new kind of steering behavior to point to. So we want our player to steer towards that point in circle. And then we want to do that every single game loop and give that kind of like wiggle effect. So that's step one. We're going to improve on the base algorithm by doing that concept. So we're going to extend a imaginary circle, but that's controlled by both a circle distance and a circle radius. And then we're going to choose a random angle between 0 and 2 pi to get to a point on that circle. And that's what we'll use for the kind of the steering force. We want to force our object to steer towards that point on the circle. Step two, the more complicated part. We want to control where our object travels by influencing it to locations that it's never been to before. The way to do that is to convert the game world into an imaginary grid, and anytime the object is traveled on top of the grid, any section of the grid, any segment of the grid, we will mark that as kind of like visited. We'll set that to a visited status. So it will randomly pick a location. The way I decided to do this is to pick the farthest non-visited location away from it. And so to make it a little bit less obvious, it will sort those. So the farthest point will be on the top of the list. The second farthest point will be on the second element in the list. The third farthest point away will be like the third element of the list. So it'll sort it by the farthest points away, and it will randomly choose one between the first element and the sixth element or fifth element, whatever we decide. So it gives it a little bit more randomness, not so obvious, where we can see, okay, the next one's going to be the top. If it's going to the bottom left corner, the next one's going to be on the top right corner. It will always be on the top right corner. It gives it some bit of a randomness. So it'll randomly pick one of the top 5 farthest segments of the grid to travel to. So once we find that, this is where it gets interesting, and I decided to implement my A-star pathfinding algorithm and kind of build upon that. So if you haven't seen or know what A-star pathfinding is, I do have a dedicated 50-minute tutorial, I think it's 50 minutes, covering that. I'll leave a link in the description below. I will be updating that and releasing a new video on that, but it's an old quality video. Just keep that in mind when you're watching it. It's back in 2010 or so. It's very old, and yeah, just watch that if you're not that familiar with A-star. I'll go over the very basics in this video, but if you want a more in-depth explanation, you can check out that video. So we need to get from our current player's location to that randomized farthest point. We've chosen where we want to travel to. Remember, our game world is in a grid now, so we can travel by segments of the grid. So we're going to implement A-star by finding the quickest way to that farthest point that we've chosen. Now, the way that A-star works is that it calculates it based on heuristic values. So it calculates it by how close the tile that you want to go to next is from the start of your position to how far that tile is from the destination, our farthest point where we want to travel to. So it adds those values together. The distance from the start to the distance to the end. And the lower that heuristic value is, the more beneficial to travel to that tile is. So that will give us a nice quick path to our farthest destination. So that's the basic of A-star pathfinding. What I did, again, I want to influence it to tiles or segments of the grid that it's never been to before. I have added more additions to the heuristic algorithm. So not only do we have distance from start plus distance to end, if the tile has been visited, if we've already been visited to that segment of the grid, I add the distance from the end again. So that turns into 2 times the distance to end if it's been visited. So that greatly increases the chance where we do not want to revisit that tile because we've already visited it. So that can come into some interesting pathing when we're just about to visit a segment that we've already been visited before, but it might appear to kind of go a longer way to the destination, but remember, it's prioritizing where it's never been to before. So sometimes that causes a longer path, but it's a more beneficial path in our algorithm because we want to wander and examine elements of our game that we've never been to before, because we're trying to search for the enemy or whatever we're searching for. We'll wander around the game world. Why do we want to wander around the same place 1,000 times? So that's the main goal. Yeah, it's going to take us longer to get to that destination point, but we're also accomplishing the secondary objective of that entire process is to visit places we've never never even been to before. So that's going to be a massive handicap to already visited tiles. It's going to greatly reduce the chances of being visited again. So back to the A-star pathfinding, we choose a segment of the grid that has the lowest heuristic value, and then we set its parent to the current lowest heuristic value, and then we will examine all of its adjacent tiles. And then we will repeat the process. We'll look at each one of those and find the lowest heuristic value and set its parent to the one we just looked at, and then we'll advance and keep on going on that. So once we examine all the lowest segments of the grid, we go backwards from the destination and we look at the destination's parent, and then that's parent's parent, and then that's parent's parent's parent, and then we're going backwards to build our path. Okay, so we always start with the starting node. That is always going to be the starting node that we need to have. The way it's set up is we have the 3 terminating states, so as long as we add the starting node in there, the open list should not reach 0, unless, of course, we cannot travel to that end node. So we set the starting node. We have that selected. That's our selecting node. Once we do that, we need to drop it from the open list and then to the closed list. So that's the first step. Now we want to see if every adjacent node, and what we want to do here is if it's not already in the open list, we add it to it. So here I'm going to add this to the open list. Now I also do my heuristics, and this is my optimized version like I talked about. So instead of getting the distance from start, for example, 8 and 7. This is the distance between here and here. So I'm only getting the distance between the parent and itself. But I'll walk you through that later. Alright, you can see what I did here. You can see the L1, L2, L3, L4, L5, L6, 7, 8, 9, 10, 11, 12, 13, and there we go. So you can see the L crossed, and that's what I did with the lowest. So lowest 0 is what we have first. Now, all the adjacent nodes, these 3. This one, this one, this one. Gather heuristics. The heuristics are from here to the end node. So, what we have here is 1, 2, 3, 4, 5, 6. So 6 in the delta x direction. So we square the change in x, and that gets us the 36 you see here. Now, between here and here, we have 1 and 2. So 2 in the delta y, so we square the change of y, and then we get the 4 here. We add those together, that's how we get our 40. Distance from the parent, which is from here to here, it's just 1 in the x. We square 1, it's just 1. So now our total is 41. Now we do the same thing. 9 and 36. We have 1, 2, 3, 4, 5, 6 in the x direction. Square that. That's 36. So that's this here. Then we have 1, 2, 3 in the y direction. Square that. That's how we get our 9 here. Add them together. We get 45. Distance from start. That's 1, 2. So that's how we get our 2. Add those all together, we get 47. Now we do the same thing with this one, we get 59. That's it. Next loop through, we need to choose the lowest one, which is this one. That's why this is L1. Now we check to see if our adjacent nodes are already added to the list. They are already added to the list, so let's check to see if our new distance is better than our old one. So what our new one does is it takes this value, the distance from start, this value here, that 1, and calculates the distance from this node to the current adjacent node. Let's say we're looking at this one. So from here to here, that's 1. So 1 plus 1, that's 2. It's not better. From here to here, that's 1, 2. 2 plus 1, that's 3. So that's not better. So we do not change any of our parents. I don't think we change any of our parents in this whole example. So what we do here after that is these two are done. So the only two left on the open list are these two. Now we choose the lowest one, which is 47. So this one is the lowest one. Now we check to see if any of the adjacent ones are already added to the list, and this one is the only one. 2 plus 1 is not better than 1. So we do not update the new distance. These 3 have not been added to the list. So you see the parents' arrows are here. So this node's parent is this. This node's parent is this. This node's parent is this. So we update the parents with the current selected one, which is this because it's L2. And then we do our heuristics again. So now the only ones that are left are these and this one. So which one has the lowest? This one. This is why it has L3. Likewise, we add all these to the open list and this one to the open list. Set the parents, so this one's parent is this one. These 3 parents are this one. Calculate the heuristics again, and we're done. We do not update any of the other ones, so we're done. Now, we need to choose the lowest one from these 3, these 2, and these 2, which is this one, which is 31. So that's why that's L4. Now, I did this on paper, so I ignored this one, because I was going to implement a way to calculate if it's surrounded by walls, do not allow the diagonal one here. Okay, just imagine that this one is a black box. Alright, so that's stuck. That's nothing. We do not have any adjacent nodes to test. We do not have any adjacent nodes to add, so that's it. What's the second lowest one? It's this one, 37. That's why that's L5. So I think you get the idea now. The only one that is not added yet is this one. So we set this one's parent to this one. This one's parent is this one. And now will be a perfect time to demonstrate it. The previous parent is here. This is the distance from the previous parent node to itself. So 4 is right here. And then what's the distance between here and here? It's 1. So 4 plus 1 is 5. Okay, so now we have this one. This one's parent is this one. So we have 5 here, and what's the distance between here and here? It's 1, 2. So 5 plus 2 is 7. So that's my optimized version. I'm not doing like 100 distance between here and here. I'm actually saying the distance between here and here, plus whatever that value was. Okay, so I think you get the idea now. Now, once we calculate all that, we got our parents set up. Remember, we have to keep an eye on these arrows, our parents, because once we get all these figured out, and once we look at the end here, we need to go all the way back. We need to say, all right, from the end's parent, this is in the path. All right, now we go to the end's parent. This is in the path. Parent, this is in the path. Parent, this is in the path. Parent, it's pointed here. This is in the path. Parent, it's pointed here. This is in the path. This is in the path. This is in the path. this is in the path, 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 and this is in the path. Okay, I hope that's a better explanation as well. Now, ideally, we want the full path when we find our final destination. We want the full path generated and we'll travel on that path. I've decided to, for this algorithm, I've decided to, every single game loop, we rerun A-star pathfinding. Because as our object travels, a new shorter path might be generated. And that also gives us another element of randomness to the behavior of our object by changing the path in the middle of its travel to that new destination. So we might go to a tile that generates a shorter path, and we will turn and go along that shorter path. And then every single game loop, we will regenerate that path, and it will pretty much always change throughout the travel to that destination. So there's many ways that you can do that. You could just have the object travel to that point and be done with it. So I decided to use A-star pathfinding to give it more of a chance to travel to locations it's never been to before. So that's the basic goal of the wandering algorithm. The basic increasement to the algorithm that we already did a few years ago is to extend a imaginary circle and choose a point on that circle by a given radius and a random angle between 0 and 2 pi, and that's where we're going to give our little wiggle effect. And then the second part is to implement a grid-based wander system where we turn the game world into a grid, and we will prioritize traveling to segments of the grid we haven't visited to yet. And then, wait, what if every segment of the grid has been visited? Well, we simply set all the visited segments back to non-visited, and we repeat the process. Now, one thing I did take out of the wandering algorithm this time around is I took out the wall avoidance, because that's going to be a separate steering behavior this time around. We want wandering just to be, the separation of concerns. We just want wandering to wander. Then we will throw another steering force for avoiding the walls. So the wall avoidance is no longer part of the wandering algorithm, because that's going to be separate now. The good thing with steering behaviors is that you can stack them on top of each other. So we will wander, we will do a wall avoidance next, and the wall avoidance will have a more stronger force to force our object to not go outside of the bounds of the game window. So it's called wall avoidance, but for this purpose, for now, it's going to be the bounds of the game window. So as we run the sample in the next video, you will see that the game object will travel outside of the game window, but it will always come back because it wants to go to that tile that we've chosen. And that's because I took out the wall avoidance part of the algorithm. So there will be some cases where the object will go outside. And that's normal for that algorithm. Alright, so that makes a much greater, more randomness looking approach to wandering. Because in the previous algorithm, there were some cases where it would just hover over on the top left corner of the screen. It would just wander that way. Or it might never reach the bottom right corner of the screen, even though it hasn't been there in 20 minutes. It still has never reached that point. So improving on this algorithm by implementing the grid-based wandering is it's going to be very good for future artificial intelligence. So we can make sure every segment of the game has been looked at when our enemy is wandering. And the good thing is about the grid-based is you can, with a little bit of modifications, you can extend on it by having like a path. Like if you want to implement a stealth game where the enemy travels along a path, you can have the enemy you can turn the enemy's path into a grid and wander along that path. And yeah, it's going to be very beneficial for always visiting unvisited tiles and to prioritize that when traveling back and forth. So stay tuned for the next video where we'll discuss the code. And that's going to be probably a pretty lengthy video. There's going to be quite a bit of code involved. I'm going to just copy and paste some, and I might type some from scratch, like get to the core algorithm and we'll type that in. I did start getting ready for the VGAI, or actually I'm going to call it PGL-AI, for the PH Studios Game Library Artificial Intelligence. So I did set up interfaces for steering behavior, and the wandering artificial intelligence is a base class, and the grid-based wandering artificial intelligence that's going to be derived from that. And so there's going to be some inheritance going on to get ready for just moving that to a dedicated library that handles artificial intelligence. So there will be some of that in there, just getting things ready for that. So that's primarily why I split it up the way I did for this just random tutorial. Alright, stay tuned for that. This is probably a little bit shorter than what I wanted it to be, but with the next tutorial that's going to be longer than what I want it to be, so that's why I decided to split this tutorial into two. I'll probably do that going forward for any new algorithm. I'll have an algorithm discussion and a programming discussion right after that, the tutorial after that. So I hope you enjoyed this video. Next video we'll go into the actual coding of it, and we will run our game and take a look at what it's doing. Another thing that I'm doing in this for the tutorials, and I'm going to take this out when I convert it to an actual library, is I implemented some drawing methods in the algorithms so we can see what exactly is going on. You can build more on top of that and give more details. I just did what I found to be most relevant in the algorithms. So I did implement some drawing functionality so we can see what's going on, and I implemented a way where we can check if the keyboard has pressed the key to display that or not. So we can toggle that on and off so we can see what exactly is going on. Kind of like a debug mode. If you've played some games that have debug mode that kind of have visual representation of what's going on and that kind of thing. So it should be pretty neat seeing the algorithm work both on its own where you don't know what's going on, and then we can just toggle what's going on and we can actually see what the algorithm is doing. It's pretty interesting. So stay tuned for that. That will be the next video, probably in a couple weeks. And we'll go from there. Probably another steering behavior after that. Thanks for watching.